Okay, let's start chapter 6 together. We're talking about the chemical reactions, understanding them better, and a lot of this chapter is about what you have learned in general chemistry 1 and 2. So first, let's see what is a chemical reaction. As you know, chemical reaction shows the compounds that they react, the molecules that react, and the new bonds that are formed to form the products. So we show the reactants on the left side, we separate the reactants and products on the right side with an arrow, and we are supposed to balance the equations, the reactions, because we want to keep the law of conservation of mass valid. So if we want to balance this equation, when we balance it out, the carbons are the same, hydrogens, you have 4 on the left side and 2 on the right side, so you needed 2 in front of water molecule. Then you created 2 more oxygen atoms, which calls for 2 in front of oxygen. On top of the arrow, you might see different stuff, like you might see H nu, which is light. You might see delta, which means heat. So if we use a catalyst, what is a catalyst? The substance or something like light that speeds up the reaction but is not going to be used in the reaction. We will talk more about catalysts in this chapter. So this is what if you use a catalyst, you will show them on the arrow. In organic chemistry, on the arrow, you see these types of writing a lot. It shows that this is the first reaction happening, and that's the second reaction on the bottom. So at this point, obviously, you don't need to know what's happening between the reactant and product, and we call them reagents. But we just want to show you that when you have a 1 and 2, and if you have more like 3 or 4, means that we are looking for the final product after applying all of these steps on the reaction. So that's what is very common in organic chemistry, showing 1, 2 on top and the bottom of the arrow to show the different types of reactions on the reactant to take it to the very final product. So the organic reactions that we are focusing on can be categorized into 3 different categories. Addition reactions, you will see them a lot as soon as we will start alkenes and alkynes chapters. In addition, the name explains the 2 substances, at least 2 substances, are added to each other to form a 3rd substance. In elimination reaction, it's very similar to what you have in the decomposition reactions for general chemistry. You see a big molecule is going to be decomposed, so some part of this compound will be eliminated from it. And the substitution is very similar to the displacement reactions you had in general chemistry. So you see AB plus CD, it seems like C and B switch their locations. So AC and BD will form. Obviously, it's a very general format just to show you what would be the form of these types of reactions. It will be more clear as soon as we start working on the practices on the next page. Let's see what's going on this practice. We keep these. I will work on the first. OH connected to the cyclohexane changes to Br. So what did I just say? OH changes to Br. Nothing else happens to the rest of the molecules. So seems like there has been a substitution happening, right? OH has been substituted with Br. Let's work on C. So what happened? It looks like chlorine has been added to this molecule. So this is obviously an addition reaction. And let's work on D also. So compare the reactant and product. What's happened? It seems like the OH and one hydrogen from here has been eliminated to form this double bond. So this is obviously an elimination. I'm sure you can work on B on your own. So we are going to start studying the reactions from 2 points of view. From a thermodynamic point of view, and from kinetics. Thermodynamics and kinetics. And this way, we will have the radical, two different mechanisms. Radical mechanisms, and we will have polar mechanisms. Radical mechanisms, we will learn them in the last chapter, chapter 13 if I'm not wrong, and polar mechanisms, we will learn them as soon as we are going to learn the alkyl halides. But we will work more, our focus is more on the polar mechanisms. So, just a quick introduction of the signs that we work with in organic chemistry. We have two types of breaking bonds. Homolysis, when the bond breaks even breaking of bond, means this is a covalent bond, right? One electron will remain on A, one electron will remain on B. So how do we do that? How do we, let's say, show that? We show it with a hook, not the complete arrow. You remember you had it in the previous chapters as well, when we were working on resonance structures. Again, because half of the bond is transferring on each atom, we show half of the arrow as a hook. Don't forget, each part has points. So we will have one electron on each. If the bond does not break, this is a radical reaction. This is a radical reaction. If the bond does not break even, we call it heterolysis. So the bond completely breaks on towards one of the atoms. So we will be left with a cation. Oops. And an anion with all the electrons. Okay? This is called or is it a reaction since you have the same word mechanism? We call it polar mechanism. And it's an uneven breaking familiar with what we call a radical mechanism and a polar mechanism. For example, if you are showing on page 3, if you're showing the mechanism for homolytic cleavage of sigma bond in H2, homolytic. In H2, we said homolytic is even. So we show the hooks, 1 electron on each, so we will have 2 radicals through a radical mechanism. If you want to show the heterolytic cleavage of sigma bond in HCl, then we know that HCl is partially negative on chlorine and partially positive on hydrogen. So the entire molecule, the entire bond will break over chlorine because chlorine is more electronegative, wants more electrons. So at the end, we will be having chloride and hydrogen ions. That's a polar reaction. And the opposite of breaking bond is formation of bond. When 2 radicals share 1 electron each, don't forget the hooks, sharing 1. So AB forms, again radical. And when 1 atom puts the electrons in the empty orbital of a cation, we will have a polar mechanism. Either way, AB bond forms, but through different mechanisms. So we have different notations, different summary of arrows. I mean, we need to know they're a little bit different from general chemistry. This arrow is the reaction arrow. We have a double reaction arrow. This is for reaction. When it's two-sided, two ways, let's say, it's for equilibrium. General chemistry 2. Means reaction can happen on both sides. When you remember this from beginning of the semester, seems like yesterday. Two-sided, this is when you have resonance structures, and when you have the curved arrow, it shows the movement of electron. It's the full arrow, complete movement. And when you have half arrow, like what you have, like the hook, it's not the half arrow, is half. It's not the full headed arrow, it's half arrow. Half is shown for when you have 1 electron sharing. Full arrow is when you have the full sharing of electrons. So you need to use the arrows, especially in the mechanisms. It's extremely important to show it. The examples that you had before is just going over the page 4, the same exact examples you have. So what's happening, you remember the attack is from nucleophile towards electrophile. Nucleophile full of electrons, electrophile likes the electrons. So carbon, if you want to show it as a mechanism, the carbon attacks the hydrogen because it has less electrons on it, and the bond breaks over bromine to form a new carbon-hydrogen bond plus bromide. And another example, the same exact thing you have. And you will see these a lot later on. These are just the beginning introduction of organic chemistry mechanisms. Again, you have a polar bond here. So which one is your electrophile? Carbon, right? So nucleophile attacks electrophile. And don't forget, you cannot violate the octet rule. So You need to break this bond over oxygen, otherwise carbon will have 5 bonds. So you will end up having this one. And I told you, don't worry, we have a lot of examples, a lot of reactions. This is just an introduction. So, working on a few of these examples on page 4. First example. I would say let's work on B. Looks a little bit more complicated than A. We are supposed to show the movement of electrons by comparing reactant to the product. This is what you have on the reactant. And in the product, you will be left with this plus OH. So seems like, since you don't see the OH here anymore, it seems like this OH has been separated. How? The double bond formed, and this is your nucleophile. This is full of electrons. So the movement is towards this bond to form the double bond and kicking OH out. That's how you show the movement of electrons. You need to show the beginning of the arrow, the destination for the arrow, exactly where it happens. The second practice, let's work on A. You have OH positive, and this time you need to show the product. So again, determine your nucleophile. Nucleophile can be one of these oxygens. There is no difference between the oxygens. So this is the nucleophile, and this is your electrophile. So, I'm sorry, the hydrogen is your electrophile. So, oxygen will attack hydrogen, and oh no, I'm sorry, the movement is shown. I'm sorry, my bad. The movement is shown. Oxygen attacks this carbon, okay, and the bond is supposed to open. All right, we go with the same thing, which is given. You have OH here, and here you have OH, right? Nothing happened to hydrogen yet. Just one lone pair, so you have a positive charge. If your question is, at this point, if your question is, how do I know what would be the charge, you know how to calculate the formal charge, so you already know that. And then, if you have the full mechanism, you will have the you will see, like normally we have an acid or water to grab this hydrogen and stabilize the charge. But this is not the case here, so we just need to know how to add the atoms to each other. Okay. So, now let's start studying the reactions based on thermodynamics. It will be a review on what you have learned in General Chemistry 1 and 2, plus what we are supposed to know for organic chemistry. You remember we had two terms, the most famous terms of thermodynamics: exothermic processes or reactions, when system releases heat. So the sign for enthalpy was negative. If you have forgotten the enthalpy and the heat and all of these, please grab a general chemistry book or look them up online. You don't have time to go over the concepts that you already learned before. Endothermic reaction is when system absorbs heat. So the sign for delta H is positive. How do we determine if a reaction is endothermic or exothermic? We need to know the heat of breaking or formation of each bond. Like for example, what you have on page 5 is CH4 plus Cl2. It forms CH3Cl plus HCl. So if you draw them, so that's what you will have. We're supposed to do something on the bonds to put an X on the bonds that are broken. So if you compare CH4 with CH3Cl, what's happened? This bond is broken, right? And also, instead of ClCl, you see HCl. So this bond is also broken. Instead, a bond is formed, CCl is formed, or CH3 and Cl is formed, and HCl is also formed. So now referring to the table 6.2, the bond for CH3 and you will see them as CH3H. The bond is 435 kilojoules per mole plus. So delta H is sum of bonds broken minus sum of bonds formed, if you remember from general chemistry. So 435 for this molecule plus, I'm just using the table 6.2. I'm not creating the data. Minus the formation of the bond between CH3 and Cl will be 351 plus an HCl is formed, so 431. If you calculate everything, it would be minus 105 kilojoules per mole. So if you want to determine if it is endothermic or exothermic, based on the sign of delta H is negative, so it's an exothermic. And which one has more energy? Don't forget that you had the energy. If it's exothermic, then means the energy level of the products is lower than that of the reactants because the reactants have lost their energy. I mean, the reaction has released heat, so reactants have more. So let's work on, we already worked on enthalpy. I'm going to page 7. You know the rest. Going towards page 7 is just a quick review. When you write heat on the product side, means the heat is a product, right? Heat is released. So delta H is, if you want to determine the sign for delta H, is minus 213 kilocalories because it's a product. It's going to be released. So which one has a stronger bonds? we said delta H is bonds broken minus bonds formed. So if the broken bonds are stronger, so the subtraction will give you a positive value. But if the formed bonds are stronger, then the subtraction will give you a negative. So when you have a negative sign, means that these are stronger bonds. Because during the formation of the bond, heat is released. So the stronger the bonds, the more the heat. Now you have for the next reaction, formation of glucose happens in our body. So when you see the heat on the reactant side, means heat was the reactant, means heat was absorbed. So delta H is positive 678 kilocalories. So which bonds are stronger? The broken bonds are stronger. So means that you have to break the bonds with higher heat. That's why we call it endothermic. So the first one was exothermic, the second one is endothermic, and you can work on the third one. Working on entropy. You remember after enthalpy and enthalpy change in thermodynamics, we had entropy in general chemistry too. What did you say about the definition of entropy? The disorder of the system or the universe. So if the sign for delta S is positive, so the reaction is favored as far as entropy. If the sign is negative, then the reaction is not favored based on entropy. And what I want you to pay attention for entropy, we have to notice, we have to focus on just gaseous molecules. So why do we say gas molecules? Because comparing between solid, liquids, and gases, which one has the most movement, most disorder? Of course, the gas molecules who move freely in random directions. So if you have such a reaction and you are supposed to compare without any value, anything, we don't need a value for comparing entropy. Just look at the two sides. Just look at the gaseous molecules. How many gas molecules do you have here for methane molecule? 1 mole, right? 1 mole gas. Is oxygen also gas? Yes, plus 2 moles of gas for oxygen. So you have total 3 moles of gas on the left side. And what do you have on the right side? You only have 1 mole of carbon dioxide, right? Because H2O is liquid. Comparing to gases, liquids, and and solids are not considered to have a noticeable entropy or disorder. So we're going from 3 moles of gas to 1 mole of gas only. Which one has more movement, more disorder? Of course, 3 moles. So if delta S is moles of gas of products minus reactants, or let's say if you're going from more gas to less gas, so delta S is going to be negative 1 minus 3, negative 2. Delta S, moles of moles of gas in products minus moles of gas in reactants. So if you're going from more to less, delta S is here is 1 minus 3 negative 2, so it's less than 0. So such a reaction is not favored based on entropy. That's all you need to determine for entropy. All right? Let's work on the next and the last factor, which was delta G. General Chemistry 2. What was it called? Gibbs free energy. For Gibbs free energy, you had a formula. Delta G is delta H minus T delta S. And temperature, don't forget, temperature is in Kelvin. Whenever you see capital T, temperature is in Kelvin. And delta G shows the spontaneity. If a reaction works, it happens spontaneous or needs a push, needs some energy. So if the sign for delta G is negative, it's going to be spontaneous. It happens by itself. If delta G is positive, so it's non-spontaneous, it needs something to start the reaction, whether heat or catalyst or something. And if delta G is 0, then the system is at equilibrium. The rate of forward and backward are the same. We'll talk about equilibrium later on. So you have a reaction on page 8. We first need to balance it. The physical states of the substances are given for the products. I don't know why it's not given in the reactant, but it makes it a little bit vague because it's important for you to know what happens. So let's balance it out together. We will need 2 gold atoms here, and you need 3, so we need 3 hydrogens also. If we consider the reaction between solid gold and liquid water, the reaction will happen from 0 moles of gas to 3 moles of gas. So let's imagine it happens. 0 moles of gas, and here 3 moles of gas. So its delta S is positive, is entropy favored. But answering if the reaction is spontaneous or not depends on the temperature and the value for delta H. So it's not that easy to answer it. And if you remember, because for delta H we have exothermic and endothermic, for delta H we had endothermic and exothermic. We have 2 terms which are similar to the terms we use for delta G. For delta G, when it's negative for a spontaneous reaction, we call it exergonic. And when delta G is positive and it's non-spontaneous, we call it endergonic. that's what we have for the delta G. So spontaneity depends on both delta H values, delta S values, and also the temperature. So in higher temperatures, delta S rules. In lower temperatures, delta H rules. So seems like we need to have more data for delta G. All right, work on this. In the next video, we will switch to the kinetics.